Hi, my name is Manish Gupta, and in this video, I'm going to talk about Codex, large language models which are trained on code. So let's get started. Codex is the main kind of models which powers GitHub Copilot. So you might have seen these kinds of demos on GitHub Copilot, where or you might have actually also used them in VS Code, Visual Studio, and so on, where the user, the programmer, sort of types in a few lines of the code, just the description of what is expected from the code, especially the docstring. The docstring part, the function definition, and then or the declaration. And as you see, it automatically completes the logic for the function. Right? This is another example about Twitter. So essentially, if you want to fetch tweets from user, it automatically gives you this template code where you can, of course, replace the appropriate or have or define the Twitter key and a Twitter token in the in the environment which this code can use. Here are some other examples. Here you're trying to essentially get rating from a particular website called Goodreads, right? So this is the entire code, parsing code. And then here is other code to draw scatter plot. So just say draw scatter plot and nicely gives you code complete, right? So what is Codex? Codex is basically a GPT language model, which is fine-tuned on publicly available code from GitHub. It powers GitHub Copilot, as you just saw in the demo. It automatically completes the code, given some declaration, some definite, some description of what to write in the code. Right? It generates Python functions from docstrings, as we just saw. There is also other efforts similar to Codex, where or other, doing some sort of task over code, and those efforts are called CodeBert and PyMT5. So if you have time, do look at them, right? But in general, the nice part about Codex is the following. On a particular benchmark data set, which these guys introduced called HumanEval, they found that the 12 billion parameter Codex model actually solves about 29% of the problems, while GPT-3 is just not able to solve them. So GPT-3 by itself is a great model, but hey, it just doesn't work on code, right? GPT-J, another model, basically solves about 11% of those problems. So essentially, Codex is pretty good for code, right? Codex fine-tuned on standalone corrected implemented function. So this Codex model is is a simple Codex model. I'll describe more in detail how it works. But then if you fine-tune this further on some more standalone functions and create something called as Codex-S, then that one can actually solve about 37.7% of the problems. So it's sort of better compared to the typical standard Codex model. Now, this is possible if you're trying to basically give the docstring input and trying to directly ask it to generate one sample, and that sample you evaluate how good it is. But hey, if you give it more chances, so if you basically do repeated sampling and you tell it, hey, you can go ahead and generate up to 100 samples, and if you get one correct, I'll tell you that yes, you're right, then it can actually solve about 70% of the problems, which is so awesome, right? So here are some of those examples where Codex has done its job, right? So essentially, the user gave a prompt, which includes the declaration of the function, and then a few examples. So that basically in the docstring, right? So that gives you the code, the generated code in the output. So everything that you see here is basically with the white background is basically inputs, and then here are more examples, more and more complicated examples, where in the yellow you see the output. So that's that. So let's talk about this HumanEval data set that they use to evaluate the Codex models, and also, the metric that they use to evaluate the models before we get into the actual models. Right? So HumanEval is basically 164 handwritten programming problems. They did not want to take actually existing programming problems from the web, because typically these GPT models, which have been used as the base for Codex, have already seen the web. So therefore, they had to literally write down themselves programming problems. Each problem actually includes the following: a function signature, right, docstring, body, and then several unit test cases, on average about 7.7 test cases per problem, so that they can evaluate based on those test cases. These problems actually assess language comprehension, reasoning, algorithms, and simple mathematics. So those are the skills that are required to be able to solve these problems, right? Now, the way to evaluate, so remember, this is a generation task, natural language generation task. You're trying to generate code. So the way to evaluate is you could use standard generative metrics like Blue, Rouge, and so on, but they don't make much sense, because, hey, I can't say that I have an awesome Blue score and therefore my code is great. And therefore, they wanted to actually test the goodness of the model based on functional correctness. Now, a very simple way of testing functional correctness is to basically ask the model to generate K-code samples, right? So take the problem definition, generate K-code samples, and then you would consider the problem to be solved if any of these samples which are generated passes the unit test. Now that's called as the standard pass at K metric, which basically is like, hey, you generate K of them, and then if any of them is correct, give you, you pass at K, right? However, this kind of a metric has very high variance, and therefore they defined a better variant. And the better variant is as follows: rather than generating k, generate n greater than k samples per task per problem, right? And in their experiments, they fixed n equal to 200 and k less than equal to 100. They measure at different values of k, right? And then the thing that you measure is as follows across all problems. Let's say in this particular problem, out of n, you got c correct samples, then the pass at k metric is going to be that where this function n minus ck is the combination function, right? So the typical permutation combination, the combination from the typical permutation combination literature. Yeah. So now how did they tune their model? So they start with the GPT model, right? They observe that using a pre-trained GPT versus a typical GPT from scratch did not give them better results, but did not show any differences. But then they still started with pre-trained GPT, right? They fine-tuned on this data set. Data set is collected in May 2020, 54 million public software GitHub repos, which is 179 GB in size, right? Where each file is less than 1 MB. Each Python file, they just work on Python. Yeah. Uh, they removed auto-generated files for filtering, right? They removed auto-generated files that looked like auto-generated ones, files with average line length greater than 100, files with max line length greater than 1,000. They did a whole bunch of cleanup, and that gave them a data set of 159 GB, right? And the training was done very rigorously for as many epochs as needed to reach 100 billion mark, 100 billion token mark. The prompt included a header, signature, and a docstring, and they used nucleus sampling for sampling the output. Um, while sampling, you try to while training, you try to minimize the negative log likelihood, and then the sampling is stopped when you meet one of these stop sequences: new class, new definition, or hash, new comment, and if and print, and so on. So as to basically say that, hey, whatever you wanted to talk about solving this problem is done, and then a new thing is starting, right? So therefore, that is where you stop. Now, what should be your sampling temperature? So they observe that sampling temperature is very important to decide for this task. And for different values of k, it's important to choose the sampling temperature appropriately. See, typically the sampling temperature actually controls the diversity of the outputs. And if you basically are using using a larger k, then you would rather use higher sampling temperatures also, right? So this is a plot which shows that, hey, as you vary k, to be able to get higher metric, in general, you need higher sampling temperatures. That's that, right? And also what you observe in this plot, sorry for the overlap, but what you observe is that if you have higher values of k, this is the convex hull obtained by looking at the previous plot. So as you have higher k, you would expect higher sampling temperatures. You expect higher sampling temperatures, right? So using this kind of a notion, they actually generate, they train their models. And then now for the metric part, right, essentially how to choose the best one. So you're still generating k, which is great, right? So pass at k is a nice metric. It is the result of sort of evaluating best out of the k samples, best one out of the k samples, where the best sample can be picked by the oracle, right? It's like you try to figure out which of them works, and then even if one works, you basically say you have passed, right? So an oracle is needed to figure that out. But for several situations, like autocomplete, you just need one good sample. So at test time, now who will decide which is that one good sample out of k, right? So now you could have several methods to select that. You could randomly select out of top 10, for example, right? Or you could basically choose the one with the highest mean token log probability, some log probability. Or also what you could do is, let's say a model generated 10 code samples. Now you would probably also train another model, which basically says, given this code sample, what is the docstring associated with it, right? And whichever has the highest probability of generating the right docstring is the one that you would choose. And now that's called as docstring-based back translation score. Okay. Now, what they observed is that as you increase the value of k, of course, typically your pass rate increases, right? However, your pass rate increases nicely with Oracle, right? Now, if you actually look at the mean log log of the highest mean token log probability, that also shows a good behavior. However, if you choose randomly or any of those other three methods, then you don't see really improvement with respect to k, right? So a very practical method is therefore using the highest mean token log probability. Now, how does this model compare with existing models? So there were some existing models like GPT-Neo, GPT-J, and TabNine, which also aimed at generating code samples given docstrings. So GPT-Neo and GPT-J have been trained on the pile data set, which is a lot of data, including about 8% of GitHub code. Right? Now, GPT-Neo, when compared, right, if you compare it with at different values of k, with respect to different codex models, they train different sizes. So from 10 million to 12 billion, right? And if you compare, you see, GPT-Neo achieves 6.4% at pass, at k equal to 1, pass at 1, while and of course it also has GPT-Neo, yeah, with k equal to 100, it has 21.37. However, GPT models are essentially original GPT model is GPT-3 model, for example, is just 0%. So essentially, GPT-Neo is still adding value. It is still doing something nice, right? However, if you notice, GPT-Neo 2.7 billion model, 21.37% is approximately the same as this model, which is about 30x less times of parameters, right? 30x less times of parameters. Also, if you notice this GPT-J model, this one, the matrix that it provides is approximately the same as this Codex 300 sized model. If you compare, of course, it's slightly better anyway, but approximately the same size, approximately the same matrix with 20x fewer parameters, which is so awesome, right? In fact, the TabNine model is approximately the same as performance as the Codex 12 million model, which is way smaller compared to those models. Okay. So in short, Codex model is actually way better compared to baseline models, both in terms of size and terms of, or rather, it can achieve the same kind of accuracy values, pass at k, with much smaller sizes. Now, as I mentioned, Codex model has been trained on GitHub Python code, which contains all kinds of things, including class implementations, config file scripts, and even files used to store data. Now, this is not really relevant when it comes to solving problems given a problem description, right? So it's unrelated to synthesizing functions from docstrings. And therefore, what these guys did was to actually train Codex-S model, which has been fine-tuned on data which is really relevant to the test set, right? So essentially, therefore, they actually found standalone functions from competitive programming websites and also from continuous integration repositories. And that is how they fine-tuned this Codex model further to generate Codex-S models. Now, again, they also tried to minimize the negative log likelihood of the reference solution, but then the idea is that they fine-tuned on specific standalone functions from competitive programming websites or from continuous integration repos. They did not take too much of data, 10,000 and 40,000 problems from these things. But they did take nicely chosen data, so such that, for example, in competitive programming cases, right, exactly the problem definitions actually match with the synthesizing functions from docstrings, right? So they are self-contained, come with well-written problem statements, and they test again, algorithmic reasoning over a broad range of core skills. Right? Continuous integration kind of repos also have similar behavior, right? So you can actually collect input and output for all functions used during integration tests. Specifically, they looked at Travis and Tox because they are the most popular CI frameworks available. And they also looked at source code from PyPy pip packages, and that is how they collected these 40,000 problems. So they removed some problems, filtered out some problems because some prompts are underspecified. So therefore, the function is something else and the prompt is something else, right? And also sometimes some problems are stateful, and therefore subsequent executions can result in different outcomes. So they try to remove those by actually doing in some senses back translation, just not back translation, but just trying to figure out with their Codex 12 billion, the best model that they had trained so far, Codex 12 billion, you take that model and just try to find out, try to generate 100 samples per curated problem. And if none of them match the test case, then you know that, hey, this is probably a vague problem and therefore don't use it fine tuning. Right? So overall, they used 50,000 problems after doing all this filtering and so on, and try to fine tune and come up with the Codex S. Now, Codex S is great. So it outperforms Codex clearly by an average 6.5% points on pass at 1 and 15% points on pass at 10, pass at 100, right? So as you see, as you increase the number of parameters, of course, the models become better. And here we have plotted Codex and Codex S, both at pass at 1 and pass at 100, right? And you observe that Codex S is 1 or 2 orders of magnitude more parameter efficient on pass at 1 and pass at 100. Right, both of them, or 1 or 2 orders smaller model that you can get with the same pass at k metric. Yeah. Now, again, the sampling for the top one that you need to do follows similar kind of guidelines when you talk about Codex or Codex S. Now, one last thing that they also tried to solve in this paper is DocString generation. The idea is that the problem is the reverse problem. So now the input is the function signature and the reference solution, while the output is DocString. You want to generate some sort of a comment saying that, hey, this is what the model, this is what the code does, right? And they call those models as Codex D. And the idea here is to minimize the negative log likelihood of the generated DocString, right? However, as you see in the results, the Codex S, which aims at generating code, is way better compared to Codex D, which aims at generating docstring, right? They observed a few problems. So the problems were first, docstring model leaves out some important detail. For example, if the code is basically um, trying to get an answer up to 2 decimal places, the docstring ignores that, or it overconditions the function name and invents a problem unrelated to the function body completely that is given as input, right? And sometimes it generates really nasty things because people write nasty things in code. That is what it has learned, right? I found this function online. Hey, this test is not correctly written, and it's not my solution. Things of that kind, right? The docstrings are not that great. Okay. Now, lastly, let me talk about hazards and limitations of these models. Codex is not sample efficient to train clearly, right? Codex has been trained on hundreds of millions of lines of code, which no seasoned developer has ever seen, but they can still write so awesome code compared to Codex, right? Codex can recommend sometimes syntactically incorrect or undefined code, and can also invoke functions, variables, and attributes that are undefined, right, outside the scope of the current code base completely. Yeah. Codex struggles to parse increasingly longer and higher level or system level specifications. So if you keep giving a lot of clauses in your docstring, then Codex cannot process them nicely. In fact, it also makes this mistakes in terms of binding variables to appropriate operations. For example, in this code, in this docstring, we are basically telling it to subtract 4 from both x and w, but hey, it just subtracted 4 from x, but forgot to subtract from w. Yeah. Now, that said, Codex is super awesome. As you saw in the demo, a lot of people, a lot of my friends are actually starting to use Codex in VS Code as GitHub Copilot, of course, in VS Code, in Visual Studio as well, right? So, but there are some hazards which must be called out, right? It can lead to over-reliance. Novice programmers may think that they are typing wrong things and Codex is suggesting the right thing, or they may just accept whatever Codex suggested without checking for semantic correctness, which is wrong, right? Misalignment. So sometimes these models can actually align with what the coder is trying to type. So for example, if the coder is trying to type a racist comment in the comment section of the code, they will just continue to do so, right? And so on. So it's sort of the model basically tries to match or align with what the user is expecting rather than actually trying to be helpful, right? Bias and representation, Codex can be prompted in ways such that it generates racist, denigratory, or otherwise harmful outputs as code comments. And therefore, some interventions are, of course, required. Economic and labor market impacts. Well, I mean, programming is a prime job for several people. But then remember, programmers don't just code things. They also, of course, do many other things. So therefore, I don't see how this kind of stuff is going to replace the job of programmer. Really, it's just assistive in nature. It's sort of I have seen lots of my students actually taking help from the GitHub Copilot and becoming very efficient at doing their work, right? Uh, well, it has security implications. It can actually generate vulnerable or misaligned code sometimes. Well, about copyright issues, yeah. So all these generative models come with some consideration for copyright issues. Fortunately, people observe that in less than 0.1% cases, Codex actually generated code that is identical to the contents of some training data. Right? But then remember, the idea is that this code was really generated in the context of what the user asked for. And like most generative models, whatever prompts you give, whatever trained data has been used to train Codex and so on, all of this just contributes to the generation of the final masterpiece that the author came up with. And therefore, the author who came up with the masterpiece actually owns the copyright, right? So essentially, therefore, even from that perspective, there's not much of a worry. So no wonder Codex is doing really well as part of GitHub Copilot. In summary, let me quickly summarize this video. So we talked about Codex. Codex is a GPT language model, fine-tuned on publicly available code from GitHub. Lots and lots of code though, right? It is fine-tuned on large amounts of GitHub code and further fine-tuned on standalone function code, right, which is taken from competitive programming examples or continuous integration repos. Right? Powers GitHub Copilot, and it has helped several people become more effective and efficient. So it reduces context switching for seasoned programmers, and thereby improving their productivity. For non-programmers, it enables them to actually write specifications and have Codex draft implementations, right? It's literally the no code scenario where you don't know code, but you can actually write the description and hey, some code gets generated, right? They as a byproduct, these guys also contributed the HumanEval dataset, which has been used in later papers also, right? And they also contributed this nice parset K improvised metric. Thanks for watching. Hope you liked the video. Here is my LinkedIn to connect with me or my homepage to know more about my research. Thank you.